Hello everyone, welcome to this course. So this is General Physics 1 Algebra based. Okay, so today is the first lecture of this course, and here I'm going to discuss about Chapter 1. And Chapter 1 is about basically the basic stuff that you need to start this course. Okay, I already uploaded the materials in the Brightspace, and most of the materials are from Giancoli's 7th edition, Giancoli's physics textbook 7th edition. Although some of the materials I copied from OpenStack's physics textbook available online. All right, so let's see what we have in first chapter. So in the first chapter, we have this. Okay, all right. So first thing is why we need physics. Yeah, of course, we need physics because we have to pass this course. Beside this, it's important to understand things around us. So here I show some example. It's basically the construction related example, but it's not only important in construction industry, it's important in many other industry also. Okay. So here you see in the left picture, top left, it's a 2000 years old bridge and it still stands. On the other hand, the top right is a bridge that was collapsed just after 40 years it was built. Okay. The left, bottom left even is a terrible example of construction failure. So it was the Hartford Civic Center in Connecticut, and it's collapsed in 1978, just 2 years after it was built. Okay. And the last one, the bottom right one, here they use a mirror. Okay, and it looks nice, but it was designed poorly. Okay, so they did not think that the reflection from the sun could cause damage in the nearby properties, and that happened. Okay, so so you see that without proper understanding of the physics or misunderstanding of the physics could cause destruction, and destruction costs money. Okay, destruction is expensive. So we have to understand physics not only to pass this course, but also to understand the things around us. All right, let's go to the next slide. And the next slide, I talk about measurement and uncertainty. So measurement plays a crucial role in physics, okay, but it can never be perfectly precise. Okay, so what I mean by this, okay, so to understand this, let's consider this example. Okay, so let's say we want to measure the length of this board. Okay, now if we use centimeter scale, so centimeter here means 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the centimeters, and the small lines between 1 and 2 and 0 and 1, these are millimeter. Okay, so if you measure this, let's say if you measure the length of this board, length of this part of this board by centimeter scale and then millimeter scale, you'll find that the measurement in millimeter scale is more precise than centimeter scale. Okay, now if we have even finer scale than millimeter scale, our measurement probably much better than millimeter scale, and so on. Okay, so that's why we say that no measurement is perfectly precise. Okay, there is always some uncertainty. Okay, if we have better technology, we can measure something better. Okay, so what now basically uncertainty means. Okay, so for example, let's say we use millimeter scale to measure this length. Okay, so let's say we want to measure this length and we use the millimeter scale. So these small things, the small lines. Okay, so if you see that we have, so 1 centimeter means 10 millimeters. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 centimeter means 80 millimeter. And then here you see that it is very close to 88 millimeter. Okay, but it's difficult to see whether it is 80, 88 or 87 or 89. Okay, so we can write something like this: 88 millimeter plus minus 1 millimeter. So when we use millimeter scale, then um, then it would be difficult to measure some length more accurately than 1 millimeter. Okay, so here, because we are using a millimeter scale, the measurement is accurate within 1 millimeter. Okay, so we can write something like this. Okay, so what it means the correct length of this part of this board could be 87 millimeter to 89 millimeter. Okay, so if we write something like this, then it would be more correct, or something like this. Instead of saying just the length is 88 millimeter, if we write something like this or this, it would be more correct. Okay, so what it means, the length is within 87 millimeter to 89 millimeter. Okay, now in many measurement, we basically interested on percent uncertainty. So what percent uncertainty means? So the definition of percent uncertainty is, so the uncertainty divided by the central value times 100%. Okay, so if we have some measurement, something like this, so this is the central value and this is the measurement. Okay, so we normally use plus minus sign to represent the uncertainty. So here our uncertainty is 1 millimeter, the central value is 88 millimeter, so we can write 1 millimeter here, 88 millimeter here, times 100%, so it's approximately about 1%. Okay, so we can say that this 88 millimeter is correct within 1%. Okay, all right. All right, next thing is significant figures. So what is significant figures? So the significant figures is the number of reliably known digit in a number. Okay, so what it means, for example, we have a number, we have this number. Okay, so this number means this has 4 significant figures. So you see 1, 2, 3, 4, 4 significant figures. Now how many significant figure this number has? It has 2 significant figure, although it says it seems it has 1, 2, 3, 4, but we do not count the initial zeros or the leading zeros. So the zeros in front of a number are called initial zeros or leading zeros. We do not count leading zeros. So although it has 4 digits, but the significant digits are 2. So this is 2 significant digit number. All right. Now the next one is ambiguous. Okay, so when we have 80 kilometer, okay, so 80, so this is ambiguous because some people call it 2 significant figure number, some people call it 1 significant figure number. Okay, so if we have some number, something like this, okay, so it could be 2 significant figure, it could be 3 significant figure, it could be 4 significant figure number. Okay, so we have to be careful here. Now to avoid this ambiguity, we have some rule. Okay, so the rule is if we have some number something like this, we do write something like this way, and the ambiguity is gone now. Okay, so if we have zeros at the end, we call them trailing zeros. So we do not count trailing zeros if it is not a decimal number. So here you see this is a decimal number. If we have a decimal number, we can count the trailing zeros. If it is not a decimal number, we do not count. So this is ambiguous, but this is not. So this number is 3 significant figure number. Okay, so this is 3 significant figure number. This is ambiguous. So to avoid ambiguity, we just put a decimal number and then add a 0, and ambiguity is gone. So now it is 3 significant, it's straight 3 significant figure number. All right, so that's how we avoid ambiguity if we have some. Okay, the next thing is mathematical operation. So how to do the mathematical operation and at the same time keep track of the significant figures. Okay, so yeah, you know, in physics often we do mathematical operation, right? Mathematical operation means we add numbers, we subtract, we multiply, we do many other complicated calculations, right? So if you want to keep track of the significant number, what to do? Okay, so when we do some mathematical operation, then the result is no more accurate than the least accurate number used. Okay, so in the next slide I'm going to talk in details about that, but before that let's talk about rounding. Okay, so if we have if we need to round off some number, okay, how to do that? So let's talk that, and then let's go to the next slide and see how to do mathematical operation. Okay, so rounding. So let's say we want to represent this number. Let's say we have a number 6.638, and I want to present it in 3 significant figure. So you see that it has 1, 2, 3, 4 significant figure, but I want to present it in 3 significant figure. So 6.63. Okay, now if we have some number something like this, how to make it 3 significant figure number? Okay, so this is the rule. So find your number, look right next door. So here right next door is this number. Okay, so if it is 4 or less, just ignore. If it is 4 or 5 or more, add 1 more. So because it is 5 or more, so the number will be this. Okay, 6.64. On the other hand, if we have some number, let's say this, then it would be just 6.63 because it is 4 or less. If it is 4 or less, we ignore it. If it is 5 or more, we add 1 to the last digit. Okay, so that's how we round number. All right, now let's go to the next slide. And here I talk about the significant figures. I mean, operation of significant, mathematical operations. Okay, now let's say we have 2 numbers, this number and this number. Okay, both are 4 significant figures. Okay, so if you do this operation in your calculator, you get this. So here you see it is 5 significant figure number. Okay, now when you do operation of when you add two numbers, both are 4 significant figure, the result should be in 4 significant figure. So you see that the correct result is this. Okay, now here you did some rounding, right? So for example, you have 1, 2, 3, 4, 5, so you want to keep the number up to 4 significant figures. So this is the 4 significant figure. And now look the next door. So next door number is this one, which is 4 or less. So you ignore it and your final result is this. Okay. So this was easy because both are in 4 significant figure. So the result is 4. It is easy to understand. But how about the next one? So in the next one, you see the first one is 4 significant figure, this one 3 significant figure. The result in the calculator gives you this, okay, 5 significant figure. But the rule says, if you go to the last slide, you see that it says the answer is no more accurate than the least accurate number used. So here in the second question, second problem, the least one is this one. So it has 3. Right? This has 3 significant figure. This has 4. So because this is the least one, the result needs to be in 3 significant figure. Okay. So here you see this is 3 significant figure. So 3. You look at the next door, which is 5 or more. So you add 1 to the last digit. So that's why it is 84.7. Okay. All right. The next one. So here you see this is 3, this is 4, this is 5. Okay. Because this is 3, the least one. Okay. So the result should be in 3 significant figures. So here you see it is 3. Okay. Again, so this is the next door number because it is 5 or more. So you add 1 to this one. Okay. Similarly for multiplication. So this is 3, this is 2. So you need to present our number in 2 significant figure. Okay. So this is 2. You look the next door, which is 5 or more. So you add 1 to here. Okay. So that's how you do mathematical operation. Okay. All right. Now calculation in your calculator. So let's say calculator, calculators don't know how to deal with significant figure. Okay. So it's your responsibility to present your number in correct significant figure. So for example, if you divide 2 by 3, okay, the calculator will give you these. Okay. So you see that it is not in correct significant figure because both are in 2 significant figure. The correct result should be in 2 significant figure. Okay. So the correct result should be 0.67. The same thing here. Calculator will give you 8, but the correct result is 8.0. Okay. So it's your job to present your number in correct significant figure. Okay. But in Brightspace, okay, when you submit your homework in Brightspace, I don't care much about the significant figure unless I explicitly mention that you have to submit your answer in correct significant figure. Okay. So if you see that, then you have to be careful. Otherwise, I don't care much. Okay. But normally, it's good to have this practice. Presenting number in correct significant figure. Okay. But don't worry about submitting the homework in Brightspace. If I explicitly mention, then make sure you submit your answer in correct significant figure. Otherwise, it doesn't matter. All right. Next, the scientific notation. Okay, so in physics, we often deal with very big number and very small number. Okay, for example, the distance from Earth to Sun is this. Okay, so you see that many zeros. Okay, the age of the universe, this big number. The lifetime of a subatomic particle. So this is a subatomic particle, and it's so tiny. Okay, you see that it's decimal and then many zeros. Okay, it's a tiny number. So when we have a lot of zeros in a number, there is a big chance to make mistake. Okay, when you write this number. So scientists develop some notation, we call it scientific notation. And if we present our numbers in scientific notation, the chance of making mistake is less. Okay, now let's see how to do that. How to write how to convert a regular number, something like this, to a scientific to a number in scientific notation. Okay, so the rule is this. Okay, so the rule is here. So let's say we have this number, and I want to convert it into scientific notation. Okay, so this is a big number. I want to convert it in scientific notation. Okay, so scientific notation is writing the number as a power of 10. Okay, so to do that, what we have to do, we have to place a decimal just after the first non-zero number. Okay, so first non-zero number is 4 here, so we put a decimal here and then write all the non-zero numbers. So here we have only 1, so I write 5 and then multiplication sign and the 10. Okay, the power of 10 will be how many digits we have here after the first significant after the first non-zero number. So after the first non-zero number, the first non-zero number is 4, and after that we have 1 2 3 4 5 6. So the power or the exponent of 10 will be 6. Okay, so this is how we write a number in scientific notation from regular number. So here 2 other examples. Let me show these examples. Okay, so here you see we have 1. So the first non-zero number is 1, so 1, and then 5 is another non-zero number, and then times 10. So what will be the exponent? So 1 2 3 4 5 6 7 8 9 10 11. So the exponent will be 11. Similarly, for this one, the first non-zero number is 4 and then decimal. So because there is no non-zero numbers after that, so you can put a 0. Okay, then 10. So after 4, after first non-zero number, we have 17 zeros. Okay, so the power would be 17. Okay, so that's how we write the scientific the number in a scientific notation when we have a big number. But then how to write a small number, how to write a regular small number in scientific notation. So here is the rule again. So when we have a number something like this, okay, so again first look for the first non-zero number. So first non-zero number is 4, and then put a decimal and then write all other non-zero numbers. So here we have 5 3. Okay, and then 10 to the power is, so here the power will be how many times you move the decimal. So you move the decimal, so 1 time, 2 time, 3 time, right? So 1 2 3. So the decimal, the power will be -3 because you move the decimal to the right. Okay, so here here the sign for the exponent, sign for the power of 10 will be negative. Okay, so similarly for this one, okay, so the first non-zero is this one, so 1 and then 482 times 10 to the power, so we move decimal 1 2 3 4 5 6 7 8 9 10 11 12 times. So the power will be 10 to the power -12. Okay, so that's how scientific notation works. Okay, so for big number, the exponent is positive. So you see that exponent is positive. For small number, exponent is negative. Okay, remember that. All right. Next is common prefixes. Okay. So common prefixes are those. I mean, there are some scientific notation are so common. Now we have some common prefixes. Okay. So so here are those. So here I put a table. Okay. Now, we don't need to understand all of them, but some of them we commonly use in this course and general physics too. So it would be great if you understand what those means. Okay, so for example, the commonly used prefixes in this course and general physics too are these: kilo. Okay, so kilo. So for example, you will see kilometer or kilogram. Okay, so normally small k is used to represent kilo, and it means 10 to the power 3. Okay, so what it means, for example, if I want to know what is 1 kilometer in terms of meter, so 1 kilometer is 10 to the power 3 meter. Okay, we will be using centimeter. Okay, centimeter is C for centimeter, and the the number is 10 to the power minus 2. The value is 10 to the power minus 2. So milli, the symbol is M, and the value is 10 to the power minus 3. Okay. So micro, we use a strange symbol. The strange symbol is called mu. It's a Greek symbol. Okay. So Greek symbol mu is for micro, and then it is 10 to the power minus 6. The value is 10 to the power minus 6. Nano, n, small n, 10 to the power, value is 10 to the power minus 9. Pico, small p, 10 to the power minus 12. Okay. And here on the other side, mega, capital M for mega, value is 10 to the power 6. Giga, capital G, 10 to the power 9. Tera, capital T, and the value is 10 to the power 12. So these are the few things we commonly use in this course. So it would be great if you understand these. Okay. All right. The next thing is accuracy versus precision. Okay, so this you basically need when you perform an experiment. Okay, so let's say you perform an experiment and you repeat the same thing 4 times. So normally when we do experiment, we repeat several times. Okay, so let's say we perform an experiment and then repeat. Our target is this yellow circle. Okay, so if all the measurements are in the yellow circle, we call it accurate. Okay, and if all the measurements are very close, okay, then we also call it precise. Okay, so for example, here for the first picture, our measurements are accurate and precise because all the measurements are within yellow circle and they are close, so the measurements are accurate and precise. If we have some situation, something like this, okay, something like this, so you see that they are within yellow line at some within some uncertainty, but then they are not close to each other. Okay, so they hit the yellow somehow, but they're not close to each other. So here we can call this measurement, this set of measurement, as accurate but not precise. Here you see that none of the measurement are within yellow, but they're very close. So this situation is precise but not accurate. And here they are neither precise not accurate because they are far from each other and they are not in yellow circle. Okay, so when you do some experiment, you will be seeing this kind of situation. Okay, so we normally want these, our measurements are accurate. We want our measurement accurate, we want accurate measurement, and also we want the precise. So if we repeat the experiment, we want the result close to our the last experiment. Okay, if so, then we call it accurate and precise. All right, so in lab you probably see something like this. All right. The next thing is the standard international unit. Also, we call it SI unit. Okay, so a standard international, also SI units. Okay, standard international or SI unit. So why we need this, or what we mean by units? Okay, so when you measure something, let's say I want to measure the length of this table. Okay, so when you measure something, you get some number. For example, if I ask you to measure the length of this table, you get 2 meters or 3 feet or 50 centimeter or something like this. Okay, so every time you measure something, you get a number in some unit. Okay, so the meter, centimeter, inch, feet, these are the units. Okay, but what we mean by standard international unit? So if everyone use their own unit, there will be mass in communication, right? So if I use meter, if someone use kilometer, another person use mile to measure the distance, so then it will be difficult to keep track of all, right? So scientific community all over the world agreed to use one unit, that is the standard international unit. Okay, although some of the countries don't use the standard international unit. Okay, but for this course we'll be using the standard international unit. Okay, so all the homework problem in Brightspace you have to submit in standard international unit, unless I stated somewhere that submit your answer in this unit, in some other unit. I mean the Brightspace expect you to submit your answer in standard international unit. Okay, so remember that. Okay, all right. Now which country they don't use standard international unit? The answer is the United States. So we are the, I mean, few countries who don't use the standard international unit to measure things. Okay, so there are a few other countries, they also don't use the standard international unit. Even though we don't use standard international unit for our everyday measurement, we for this course you have to use standard international unit, okay, or SI unit. So what are those? The standard international unit or base units are these. Okay, so here this table shows you the fundamental units. Okay, so here I show 7 quantity and their corresponding units, and the symbol we use to represent them. Although I show here 7, but only 3 we need for this course, and the rest of them we need for the general physics 2. Okay, so let's just talk about these 3, the first 3. So length or the distance we measure in meter. So meter is the standard international unit for length or distance. Time is in second, and mass is in kilogram. Okay, so mass is in kilogram, time is in second, length is in meter. As you know that these can be measured in many other units. Okay, but the standard international units are these. Okay, so these are the fundamental units. We call them fundamental because all other quantities or all other units you will be learning in this course and in the next course can be derived from these 7 quantities or these 7 units. Okay, so because all other quantities are can be derived from these 7 are called the fundamental, and the rest of them are called a derived unit because they can be derived from these 7. Okay, so in the next slide you see a set of derived quantities. Okay, so for example, in next chapter you will be learning velocity or speed. So you see that the velocity can be derived from distance and time. Okay, so and then acceleration. So you see that acceleration can be derived from velocity and time, and velocity in turns can be derived from distance and time. So acceleration is basically can be derived from distance and time. Okay, so all are there. I mean, you will be learning most of them in this course. You will see that they can be derived from mass, time, and distance. Okay, so that's why these quantities, okay, these quantities we call the derived quantities, and these 7 quantities we call the fundamental or base quantities, and their units are fundamental units. Okay, all right, so unit conversion. So unit conversion, we need to convert unit from one unit to another unit. For example, some of the problem may be given in some of the quantities. In some problem you will find some quantities that they are not in standard international unit. Okay, now because bright space prefer numbers in a standard international unit, to do the calculation you have to convert the unit not given in standard international unit to standard international unit. Okay, so not only here, in many purposes we need to convert measurement from one unit to another unit. Okay, so here I'm going to show how to do that. Okay, so here I'm going to show one example, and in the next lecture we'll do some more examples how to convert units from one to another. Okay, all right, so here I want to convert 20.15 inch in centimeter. Okay, so although they are not I mean, none of them are standard international unit, but if we know how to convert from one unit to another unit, we can use it for general purposes to convert from one to another units. Okay, all right, the first thing here you need is the relation between inch and centimeter. Okay, so the first thing, if you want to convert from inch to centimeter, the first thing you need is a relation between inch and centimeter. So your textbook, the front page, I think first or the front or back front page gives you some conversion unit. Okay, you can find the conversion between inch and centimeter there, and many other. Okay, not only between inch and centimeter, many other conversion unit you can find there. Okay, so for example, this I get from there, and it says that 1 inch equal to 2.54 centimeter. Okay, now once we have that, once we find that, the next thing is to write a fraction of 1. Okay, so how to write a fraction of 1? So fraction of 1 is this. Okay, so we divide this side by 1 inch and this side by 2.54 centimeter, and that is 1. Okay, because they are the same thing, dividing something by the same value, it will give 1. Okay, so I divide 1 inch by 2.54 centimeter because they're the same thing, it gives me 1, and the same thing here, 2.54 divided by 1 inch, it's again 1, because something divided by the same thing. Okay, so now this is the fraction of 1. Okay, so this is the second step. Now once you have this fraction of 1, the next step is to perform the calculation. Okay, so to perform the calculation, so you see this I want to convert in centimeters, so this I write this and I multiply by 1. So anything you can multiply by 1, okay, without changing the value. So when you multiply something by 1, it gives you the same thing. Okay, so 20.15 inch times 1 is basically 21.5 inch. Okay, now I can replace this 1 either by this 1 or by this 1, right? Because 1 is equal to this or that. But we have to choose carefully so that we can cancel inch with inch and our result will be in centimeter. Okay, so because here the inch is in the numerator, we need inch in the denominator. Okay, so because we need inch in the denominator, this is the correct choice, right? This is the correct choice, because inch in the denominator, so we can cancel inch with the inch. So this inch cancel with this inch, then you multiply these two, and then after correcting for the significant figure, you get 54.6 centimeter. So 21.5 inch is equal to 54.6 centimeter. Okay, so we'll be doing some more example in next lecture. Okay, so the last topic in this chapter is the dimensional analysis. Okay, so what is dimensional analysis? Dimensional analysis is a technique used to check if an algebraic expression or the result of a calculation is correct. Okay, so in any equation, the dimension must be same on both sides of the equation. Okay, not only that, each term in an equation should have the same dimension or same unit. Okay, if not, then the equation is not correct. So by analyzing the dimension, or by analyzing the unit of each term, we can tell that an equation is correct or not. Okay, and sometimes dimensional analysis is also important to determine the unit of an unknown quantities, unit of an unknown quantity from known quantities in an equation. Okay, so yeah, we will check one example in the next lecture. Okay, normally for this course, for General Physics 1, we need these 3 dimensions. Okay, mass, distance, and time. And mass is represented by these capital M and then square bracket, distance by square bracket inside L, and time is square bracket and T inside, capital T inside. Okay, so you can see a list of dimensional formula here. You see in the 3rd column. So all these quantities you see are represented using M, L, and T. Okay, and in this course we basically use these 3 things. Okay, all right. So we'll be doing at least one example in next lecture. Okay, all right, so that's it basically for today, and in the next lecture we will be doing some we will be solving some problem related to the concept we just learned in this lecture. Okay, all right, so that's it for today.